Assalamu alaikum. So in this video I will talk about how unit cells are generally created in AtomSK. Firstly, I will go through a bit of theory. What is crystallography? So this is mainly how crystals are formed. So if you have two atoms, they will stay at a minimum distance from each other. The same goes for 3, 4 or 6 atoms. They will always try to maintain a particular distance between themselves. But however, in our nature, matter are created of millions of atoms. So do they always maintain such particular distances in case of every two atoms? This is not actually practical. So what is seen that for a larger number of atoms, polygonal geometry is no longer a recommendable method for displaying the lowest energy state, because it becomes too complicated to replicate efficiently in nature. So the arrangement can be thought of as successive two-dimensional layers. So we see that here, when the atom numbers increases, they actually stack up one upon another as form of layers. And we will be talking about two particular kinds of layers which are mostly found in nature. Firstly, square packing. Here we see that atoms are stacked perpendicularly, one atom above another atom. And in case of hexagonal packing, what happens is the third atom is placed above the gap of the first and second atom. So we will be talking about three forms of crystallography, that is BCC, body centered cubic, FCC, face centered cubic, and HCP, hexagonal close packing. At the bottom of the three figures, you will see that there are three different kinds of elements which generally opt for these structures, but you have to keep in mind that these are not concrete. Upon various conditions, they may change the structure they are forming. This is more like a generalized case. So you see the structure here. In case of BCC, there is an atom in the center of the cubic. In case of FCC, there is an atom in the center of each face of the cube. And in case of HCP, we see that there are two hexagons, one placed above another, and in the middle there is another layer. So by the three circles, red, green and blue, I have separated the three layers. Okay, so here you need to familiarize yourself with two definitions: atomic packing factor and coordination number. What is atomic packing factor? It generally means the fraction of volume in a crystal structure which is occupied by the atoms, and the coordination number is the number of nearest neighboring atoms of a crystal center of the central atom in a crystal lattice. So you can count this by yourselves, which is very easy. If you take the BCC here and you take one particular atom like this one, and if you count that how many neighboring atoms it will have, you will see that the number is 8. So all this was theory, and now I will go how you can use this into creating your own unit cells in AtomSK. So the syntax is you use AtomSK to call AtomSK. Next, you use a mode named create. Then you go for the lattice type. Then the A and C means the lattice parameter. However, you see that there is a third bracket in case of C, which generally indicates that C may or may not be used. Again, SP1 and SP2 indicates the element types that are used. You will see that there is a third bracket in case of SP2 and SP3, which means that these are not required. That means a cell can consist of one atom or more. The orient means the crystallographic plane directions, which I will go in depth after a bit later. And you see that the output file is present here. That means you can specify what kind of output file you need. In case of nanotubes, you will see that after create, it is said the nanotube, which means the lattice type is nanotube. A0 means the lattice parameter, M and N means the chiral indices, SP1 indicates the type of element you are using, and finally the output file indicates the type of output you are wanting for this particular structure. So here is a bit about the lattice types present in case of AtomSK. You will find this table in the tutorial section of AtomSK website. you see that if you want to call simple cubic, you will find that here SC code word is used, and the number of lattice constants required is only 1, which means the A, and the number of atom species is 1. You cannot use 2 in case of simple cubic mostly. So in this way you can use 2. It is the minimum or the must requirement or the requirement for the simple cubic. So if you go into lattice parameters, what does lattice parameter actually mean? It means the distance between two neighboring atoms in case of a lattice. This is the generalized calculation for a BCC, and in case of hexagonal prism you will see that there are 7 atoms in the bottom layer, and the distance between each atom can be defined as A or B, but the distance between the first layer and the second layer is defined as C. So we see that to define this HCP structure we actually need 2 parameters, one is A and one is C. So in the table now you can see that in case of HCP 2 lattice parameters are required, and now you know the reason why. So what does crystallographic orientation mean? I have taken this definition from Quora. So you see that mostly you can think of the planes in the terms of the combinations of atomic spacings and how you can choose to slice them into planes. So it is very simple actually. If you take a particular matter and you want to slice it in such a way that no atoms are actually divided or sliced up, you only slice the plane between them. So in this way you can understand how crystallographic planes or how crystallographic orientation actually works. So basically how the atoms are arranged with respect to the Cartesian planes. So how do you calculate these Miller indices? In case of this structure, if you think that the blue marked region is the plane, so you need to first calculate the intercepts. So in case of x-axis the intercept is 1, y-axis the intercept is 1, and since it doesn't intersect the z-axis the intercept is infinity. By the reciprocals of these values you find that the Miller indices is 110, and in the similar way you can find the Miller indices 200 for the red marked region. So how do we use all this into creating our systems? So in case of cubic systems you will see that an orient keyword is used, and you must remember that this orient is not to be mixed with the option orient. In case of option orient it actually means to rotate the crystal, and in this case orient is used to define the crystallographic planes of the crystal. So not the same thing. The Miller indices HKL are used after orient, which is generally reduced to the smallest values. For example, you are using 2 to 2, so what it will do is it will use 111 after dividing it by 2, and it happens to all the values. Particularly for BCC, if HKL are odd then it is replaced by half. That means if you have 357, you will see that after reducing it to the smallest values an extra half is multiplied. So why is this half multiplied? And you will see that the similar case happens for FCC diamond, zinc blende and rock lattice, where if HK is odd and L is even then it will be replaced by half. So why does this half come? It comes mainly because of this symmetry that is formed by these two kinds of structures, which is, you can find the derivation online. I will not go into that. So here there are a lot of examples for the formation of cubic systems, which all of the examples you can find easily in the tutorial section of AtomSK. In case of hexagonal lattice, you see that there are 2 types of orientation. Firstly Miller-Bravais and secondly Miller. So in case of Miller-Bravais you see that there are 4 coordinates or 4 numbers h, k, I and L, where the requirement is the first 3 numbers h, k and I, they need to have a summation equals to 0. So why exactly? This is mainly to maintain the 6-fold symmetry of the hexagonal structures. In case of HCP, what happens is there is no orthogonal vector like the cubic system. So what does the vectors represent actually? So if you can think of 3 vectors required to identify the hexagonal lattice, the first vector will go along the x-axis, the second vector will stay on the xy plane and the third vector will come out of the xy plane. And in case you need to make the hexagonal lattice orthogonal, you can use the option orthogonal cell to make it into an orthogonal cell. Here are different examples which I will be going into shortly. And finally, nanotubes. So what are nanotubes exactly? So you see here there are different examples of nanotubes, and you might already have an idea what nanotubes mean. So in case of nanotubes, you need to specify lattice parameter, which is the distance. In case of this structure, you see that there are many atoms, and the distance between two neighboring atoms is mainly the lattice parameter. And after the lattice parameter, you need to identify or define two chiral indices m and n, which mainly affects its properties, the properties of the carbon nanotube. So chiral indices mainly indicate the chirality of this nanotube, and it is clearly defined along z-axis, and moreover in the xy plane it forms a replica of hexagonal lattices. So now I would be going into demonstrating each of the type of the lattices. So firstly, I will go into this one. I will be creating a cubic system. So I will open the terminal, and here you can use this code. In this code you can see that AtomSK, I am calling the AtomSK. This create is the mode, FCC is the lattice type, 4.02 is the lattice parameter, aluminum indicates the element type, orient indicates the orientation of the crystallographic lattice. The duplicate means how many types will your unit cell duplicate, mainly 40 times along the x-axis, 30 times along the y and z axis, and finally the last words are the output format. So you see that here our structure is created. Now I will be visualizing this in Obito. I will take the aluminum supercell.cfg, and you see that this is our structure, and you can easily see that this is an orthogonal, the planes are orthogonal to each other, and if you go into the depth you will find how the atoms are actually oriented in the particular way the system mentioned. So I will go to the next example of HCP. So in this example you can see that I am creating a HCP structure which is a lattice type. You see there are two lattice parameters here, A and C. Mg indicates magnesium, which is the element type. Orient indicates the orientation, and you see it is in the HKIL format, where the first three numbers HK and I, the summation of these three numbers equals to 0 in all the cases, and CFG indicates the output format. So our structure is already created, and I can now visualize it in Obito. So you see this is our structure, and you see that the planes are not orthogonal to each other, and if I would have used the orthogonal cell option, our planes should have later oriented orthogonally. Now I will create a nanotube, and I am using this example. Here you see that after the nanotube lattice type is defined, the first number is the lattice parameter 8 and 8. It indicates that two chiral indices m and n. C indicates that this is a carbon nanotube, and finally the lattice parameters. So you see this is mainly the xy plane of the nanotube, and if I visualize the structure, you see this is only in the xy plane. You will only find the full lattice, you will only find the full nanotube if you duplicate it along the z axis. So this is all for today's video. Thank you.